Real quick before we start this video, I want to go over a quick roadmap that I sketched out of nowhere. The only reason for that is LT Strange on GitHub reached out and wants to contribute, and that's so cool. Thank you, LT Strange, for reaching out. Very excited about that. It's a little early for contributing to this project, but I wanted to start laying out some type of plan so that if more people want to contribute, we can start to see where the project's going. And if there's branches like this, then that's where we can start to have people working on more than one thing at a time. But we're still kind of laying the baseline down. So in this video, we're going to talk about concatenating waves into a single file. In the big picture, let's stick with Python for now. Eventually, if we really get into this project and we start hitting performance issues, we can re-implement in something like Rust or C++. I think Rust, it would probably be pretty challenging, but it would be cool. So why not? So that's the big picture. And then the day-to-day videos, I think someday we might want to have a GUI for this, a front end. So there's a whole bunch of stuff that we could do once we get the initial base window to pop up with an open project dialog, and then we parse the config and then display each part of the song in its own component perhaps. And another thing that we can do once we load the project is to just invoke the render function that we'll already have implemented under the hood as a result of some of this more back-end type work over here. So after we do waves in this video concatenation, some stuff that we might want to do in the future is add support for chords instead of all sequential notes, add support for samples, rendering samples arbitrarily throughout the song. Buffered render, I would assume we're going to be just allocating an entire NumPy array for the length of the song to begin with. Eventually, I would assume that we would want to do that in a buffered way so that we're not taking up tons of memory if you want to render a really long song. And then eventually it would be cool to load instruments from Git repos. This was part of an idea that LT Strange proposed, is that instruments should be separate from the song, which I think is a great idea. So maybe eventually we can get it so that it'll just go out and grab all the sample data from a Git repo if you provide a Git URL, which I think would be really cool. So that's the roadmap. Let's jump into the video. Welcome back to the Plaintext Digital Audio Workstation series where we're coding up a Plaintext DAW. I'm pretty excited, and let's jump right into it. Where did we leave off? We can load the config now, our Plaintext config, or our Plaintext project file, and we can iterate all notes in all patterns. Iterate just means that we're printing them out. So we have fancy dynamic Python objects holding our config now, which is wonderful. What is next? Assume all notes are sequential and write to the wave file one after the other. So exactly what we're saying here. Going to assume these notes that we're iterating are intended to come one after the other, and we're just going to concatenate them, throw them one after the other into a wave file. That's about the simplest MVP for a DAW that I could think of, is just putting a bunch of notes in a certain order and rendering it to a wave file. So how are we going to accomplish that today? We're going to get a wave file, one of the samples that we have for the piano, into a NumPy array, probably using the wavelib. Then we're going to write that NumPy array to a file by itself, to a wave file. So basically, we could just use shell utils and do a copy, but we're going to go, we got to get it in this intermediary format where we can manipulate the raw data. After that, we're going to have to figure out the details of concatenating more than one wave file sequentially using NumPy. So I think that's going to involve calculating the full length of the song at the end of the day, which maybe we can define that in the project or calculate it by the number of files plus the length of each file or something like that. And then we'll have a NumPy array of that length with raw data, and then we can just add in the data for the files. We can literally add them to the raw data because it's just a bunch of floating point numbers from my understanding. So we can take all of the values from whichever files we're trying to concatenate and literally just add them like they're numbers. We'll see if that actually works. It's a theory, but we'll see how it works in practice. So let's jump into some coding. Okay, here we are in the code. I have to do a little experimentation, so I'm actually going to just check in as I make progress. So here I go. Okay, so some minor progress. This loads up the path to the actual sample. It's pretty messy, right? We have to go into the pattern, into the instrument, into the samples, use note value as the indexer, and then path under that. So this could use some work. And then we use the wave library from Python to open up the sample. We get the number of samples and we get the actual raw data. And we print the first 100 bits of raw data, which you can see down here, and the number of samples. So I think this is a big step forward using this Stack Overflow answer, which shows us also how to get it into NumPy. So I'll probably do that next, get it into NumPy. And then once it's in NumPy, we can really start working with this. Okay, so I installed NumPy in the setup.py and just basically followed this answer. Thanks to whoever wrote this answer. And now we have the audio in a NumPy array. Okay, so this got a little bit crazy. I'm going to walk through this mess of 25 lines or however much it is. So we open the sample just like before. It turns out we had to read a bunch of metadata about the sample so that we could write it back later. So this, in a nutshell, this goes from read the file in and dump the file back out with no changes for each file. So we'll see that that works in 1 second. Actually, let's just look at it working now. So if we run Plaintext DAW, pass in the song, we get an out folder, which it's using here. It's just joining the sample path with the out folder. And if we play these files, they are playable WAV files. So that's good. We passed these two files through our system without changing them. But the good part is that we get this normalized audio array right here in the middle. And this is where we can start making some changes or concatenate it to another NumPy array or whatever. So a lot of work to get it opened and normalized, a lot of work to get it back into an audio file. But finally, we have a NumPy array that we can manipulate with raw audio. So I think this is a big step forward. So basically, yeah, we have to get sample width, sample rate channels, all that stuff. We have to convert to normalized audio, thanks to that Stack Overflow for figuring out how to do that. Then we convert it back by just doing the inverse of these operations. So we multiply by the max int 16 to unnormalize it. Then we get the raw audio by converting back to int 16 from float 32. We make the out directory. We open with the built-in wave module. We set the channels, the sample width, the frame rate, and then we just write frames passing in our data array. So now let's get down to business with concatenating these two together. Then we'll really have something good. But for now, I will commit this. Okay, we've done it. This is big. I'm going to delete the old song.wave. So what are we doing here? We have song data, empty NumPy array, one dimensional. Then right here in the middle of the sandwich of decoding and re-encoding, instead of just printing audio normalized, we concatenate it with song data, which at first is empty, and then on the second note, it has the first note. So we end up with the two notes smushed together into this song data array. Then I unindented this block of code, and instead of converting audio normalized back, we convert song data back, and that's outside the pattern. So it's the same, method, but we're outputting this song data array that has our two sounds put together. Very exciting stuff. So if we run this, we get song.wave, give it a listen. Ah, wow. Amazing. Two notes put together by a plaintext DAW. That is so awesome. So I'm going to drop it right there. That's a video. That's number 3. Thanks for watching. Tune in for the next one.